Hello everyone, this is the prototype that we built for our project iSWaMS, which means IoT and CPS enabled smart waste management system. And as you can see here, we have used ESP32 as our node MCU here, and this is the bin that we have developed for our smart bin. And inside the bin we use three sensors: HCSR04 as an ultrasonic sensor that measures bin fill percentage. This is the DHT22 sensor that measures humidity and temperature inside the bin, and this is the flame sensor that measures any accidental flames that may happen inside the bin. And these are two MG90 servo motors that aid in opening and closing of the bin accordingly. And this is the RFID RC522 module that we used so that we can detect input of entry and exit of RFID tag, which will help in opening and closing of the bin accordingly. And this is the high precision version of Neo 6M GPS module that will help in collecting the GPS coordinates of the bin and send location accordingly. And this is the PWM servo driver that is further connected to the MG90 servo motors that help in controlling of opening and closing of the lid. And this is the MB102 power module that supplies power to both Neo 6M and also to the LoRa RA02 module. And finally, as you see here, this is the LoRa RA02 module that transmits the telemetry from all the sensors at a frequency of 433 megahertz. And so this is the final prototype that we built for our project. Thank you.
Coming to the coding part is divided into two sections: transmitter section and receiver section. The transmitter section covers the code for reading the data from multiple sensors, actuating the servo motors on scanning the RFID tag, managing RFID based entry and exit logic along with the global inactivity timeout, sending the necessary sensor data to the receiver LoRa node in a cyclic manner. Critical alerts are also sent to the LoRa receiver and are given priority over the normal packets. Sending the parameters and alerts to the ThingsBoard cloud using Wi-Fi and MQTT is also included in the transmitter side of the code, while the receiver side of the code consists of receiving the data in a cyclic manner and displaying that data over an LCD display, activating a buzzer in case of alerts. A few of the notable features of the code include usage of same SPI bus for both LoRa and RFID. This was done to minimize the pin usage and to reduce the hardware complexity by avoiding the requirement of additional SPI controllers. Cyclic LoRa packet transmission is done to overcome the 255-byte max payload limit of the LoRa modules, since the transmitter telemetry is well over 400.
Hello everyone, this is the user interface of the MQTT dashboard that we are using for our project iSWaMS. If you look at it here, we are using a website called as thingsboard.cloud to monitor all the telemetry of the smart bin. And this is the section that we are going to see all the telemetry. And if we click on this here, we'll be redirected to a separate page. This is the bin fill level percentage of the bin. This is the temperature gauge, and this is the humidity reading of the bin. So if you look at this table here, this will show the digital readings of all the different parameters of the smart bin. And if you look at this table here again, this will show the alerts of the smart bin. Here 0 indicates that there is no alert, and here 1 indicates that there is an alert of the smart bin. And if you look at it here, this is the serial monitor of the smart bin here. We can see the initialization status of each and every component here. And if you look at it here, we can see that the MQTT payload is being transported to the thingsboard.cloud, and also LoRa payload is being also sent to the receiver end of the smart bin.
Hi, my name is Nagraju. This project presents a machine learned assisted vehicle routing problem for smart waste collection. Smart bins are continuously generate data such as ultrasonic fill levels, timestamps, and GPS coordinates. Using historical sensor data, a regression-based machine learning model estimates waste fill rates and predicts the time remaining before bins overflow. Based on these predictions, bins are classified into priority levels. Only high priority bins are selected for collection, which reduces unnecessary trips and optimizes resource usage. The selected bins are then processed by a multi-vehicle routing model. Real-world distances between bins are calculated using the Haversine formula, ensuring accurate geographic routing. Google R tools is used as optimization engine to minimize total travel distance while considering vehicle capacity and depot constraint. Finally, optimized routes are converted into Google Maps, navigation links, and automatically dispatched to drivers using WhatsApp automation. This enables real-time execution of optimized routes without manual coordination. Overall, the system integrates machine learning, optimization, and automation to provide an efficient and scalable smart waste collection solution. Thank you for the opportunity.